Here's what I want you guys to do today. I posted the answer key for free body diagram day 2. So definitely take some time to look over that. We will pick up the pieces on Monday, but look over those answers, and this is the next step, is incorporating numbers into the setup. So if you can get the setup, that's going to set the stage for putting in numbers. But you need to know one more big fact, and then I'll give you some examples, and I'll post that the next worksheet, which will be due on Thursday, because we have fall break Monday and Tuesday. So here we go. So the units that make up a Newton. So if we look at the Newton's second law, the net force is equal to mass times acceleration, and Newton is equal to a kilogram times meters per second squared. That's where Newton comes from. So on Earth, we have everything experiences the same acceleration of gravity. We have a variable, g, that represents that. So this is the acceleration due to the force of gravity. So the force of gravity is F sub g. This is g, and this is g is equal to the absolute value of the acceleration of gravity. And so it is equal to just straight up 9.8, no negative. Because it doesn't have direction, it's just a magnitude. Okay? So it's 9.8. So another name for weight, we've already discussed this, is the force of gravity. It is the same thing as weight. Okay? The SI units, because it's a force, is in newtons. So in physics, we measure a weight in newtons. So how do you convert between mass and weight? We use this equation. So force of gravity, or weight, is equal to the mass times 9.8. So this is how you dance between kilograms and newtons. Okay, using this conversion by multiplying by 9.8. Okay. So the difference between weight and mass, so this is force of gravity. So if gravity is acting on it, you've got weight, but mass is independent of if you have gravity acting on you or not. This is just the amount of substance or matter. Okay, that's how much stuff, how many molecules there is. So in outer space, you could be weightless, but you could take something that's really massive and like go like this, and it would be really hard to do because there's inertia. So the inertia still exists with mass, but no, it can still be weightless. Okay, so converting between kilograms and newtons. So if there's 1 kilogram, that's going to be equal to 9.8 newtons. So a kilogram is definitely bigger. So 1 pound is equal to 4.4, well, we'll just say 4.5 newtons. Okay, so which is bigger. Pound is bigger, and 1 kilogram is equal to 2.2 pounds. So a kilogram is bigger on Earth. Okay, so just some connections with what you've been exposed to. So you could figure out how much, how many newtons you are by taking your pounds and multiplying by 4.4. 4.5. You could also take your kilograms and take your pounds divided by 2.2. Okay, so those are the factoids. This lesson, by the end of this lesson, you'll be able to convert between weight and mass, which we just talked about, incorporate numbers into the free body diagram setup, and to use that and to compare forces. Okay, so what I want you to do is I want you to, hopefully you've already checked the answers. If you have not checked your answers, your free body diagram worksheet, press pause now. All right. What I want you to do is I want you to do the setup of this scenario. 60 kilogram crate rests on a 32-degree incline. How much friction is present? Keep it at rest. So go ahead and pause the video and do the setup. So your free body diagram should look like this. And because we're on an incline, we're going to tilt the axis. Whatever this angle is, 32 degrees, that's the same angle here between the new y-axis and the force of gravity. So I'm going to make the positive direction is down the ramp. That's just, it doesn't have to be that way. It could be up the ramp, and I'm going to make perpendicular to the ramp the y direction as well. So I'm going to look at some of the forces in the x direction are equal to 0. Why? Because it's at rest, both in the x and in the y direction. So is equal to 0, both in the x and y direction. So I now need to add up all the forces in the x and the y direction. So I've got friction is going in the negative x direction, and I've got some part of gravity. It's not all, but it's some. If this is hard to like draw this triangle, so this would be the y component, FGY, and this would be the x component, FGX. You could also draw it up there, FGX. Okay. Make sure your x component is parallel to your x axis right here. Okay. So we've got FGX going in the positive x direction, and all that is going to be equal to 0. In the y direction, we have normal force going in the positive y direction, minus FGY, and that's equal to 0. Okay, so that's our setup. We haven't touched any numbers, but now we're going to incorporate numbers. So how much friction is present to keep us at rest? So I'm looking for friction. Friction is my, that's what I'm looking for. So if I could figure out what FGX is, I've got an expression that can tell me it, because I can say, okay, well, FGX is going to be equal to the friction. I'm like, that seems like a pretty good strategy. So I need to figure out what FGX is. So I'm looking at my numbers and I'm like, okay, what is 60? Is that FGX? No. Is that force of gravity? Like, oh. What unit is force of gravity? What unit is force? We have kilograms. Is that the same thing as force of gravity? No. Weight and mass are different. Kilograms is mass. So how do we convert between mass and weight, force of gravity? Well, we use this equation that we just talked about. Mass times 9.8 is equal to force of gravity. So I'm going to take this guy and multiply it by 9.8. Okay, so something to use this equation, you don't have to be in free fall. It's just this works when we're on or near the surface of the Earth always. It's just a conversion. It's the equation to convert between weight and mass. I'm going to take this and calculate this. Find that to be 588 newtons. Okay, what do I do with that? Can I stick that in for FGX? No, that is this. That's the hypotenuse here. That goes there. In order to find FGX, I need to do some trig. So what I'm going to use, sine or cosine, to find FGX. So do not memorize. Do not fall in the trap of going, oh, it's X. I'm going to do cosine. Like, look at your triangle. We're looking for the green side. We're looking for the opposite side of that angle. So we're going to end up using sine. So sine of 32 is equal to FGX over 588. So I'm going to end up multiplying 588 times sine of 32. And what I get, FGX, 32 degrees, equals 312, rounding that, newtons. So once I've got that, that is the same thing as, I can substitute that in here, and that is how much friction I need, and that's your answer. Okay. So another problem. So a fan cart experiences 7 newtons of force from fan, 2 newtons from friction. How far did it travel? What? 3 seconds. I don't know what to do with that. Like, stop. Just set up the problem. Do your free body diagram. So pause. Try to set up the diagram as much as possible. So you've got applied force, friction, normal force, and force of gravity. I'm going to make towards to the right positive. I'm going to say that's moving to the right. Up positive, so I'm going to say net. Some of the forces in the x direction, are they equal to 0 or not? Well, if it started from rest and is now moving, then inertia is not doing what it wants to do. It's not happy. So not equal to 0. Some of the forces in the y direction, are they equal to 0? Yes, they are. Because it's not moving in the y direction. It's not moving up or down. It's just going, okay. So we've got applied force minus friction is equal to mass times acceleration, x direction, and normal force minus force of gravity is equal to 0. Okay, so that's my setup. How'd you do? Okay, now we can start incorporating numbers. I'm like, all right, so how far? I'm like, I don't see anything about distance in my setup here. Well, what do we have that in our setup that is related to motion? Ding, 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 ding. Acceleration. I'm like, maybe we can find acceleration. So I've got, okay, so I've got a number for applied force, and I've got a number for friction, and I've got a number for mass. So all I can do, I can find acceleration. So I got 5 newtons here divided by 0.75. And so I've got 5 divided by 0.75. And I find that to be 6.67 meters per second squared. Now what do I do with that? Well, we can then take that and look at our kinematic equation. So I've got acceleration is equal to 6.67 meters per second squared. I'm going to say it's going in the positive direction, and I had an initial velocity of 0. I start at rest, and I need that time to go for 3 seconds, and I'm looking for how far did I go. Interesting. Look at that. And so then I'm gonna move over here. I've got, looking at my kinematic equations, I think I've got enough information to plug it into here. And so this goes to 0 plus 1/2 times 6.67 meters per second squared times 3 seconds, and I need to square the 3. And so I take times 5 times 9 equals 30 meters. Okay, so incorporating everything, setup and kinematic equations. Crazy. So I'd say that should give you enough information to try to figure things out on the worksheet. So hope you guys have a great fall break, and catch you on the flip side.